Linear transformation. In this video, the learning objectives are seeing matrices as linear transformations and their properties. Examples of linear transformations. The outcomes are verifying if a transformation is linear and using matrices as linear transformations. We can think about a matrix as a linear transformation because it satisfies two properties that we need for transformation to be linear. These properties are: 1. For any vectors a and b, if we apply the transformation to the sum of them, equals to applying the transformation to a and b individually and then adding them up. 2. For any scalar c, multiplying c before and after applying the transformation produces the same result. We can verify these properties in Julia. We define our transformation T, which is a 2 by 2 matrix. We define vectors A and B and a scalar C. We now apply T to A and B individually and add the result. We see that we can get the same result in both cases. And if you check in Julia, it says x1 and x2 are equal. Now let's check the second property. We multiply A by C and then apply T. Next, we apply T first and then multiply the output by C, and we get the same result. Some examples of linear transformations are scaling, reflection, projection, shear, and rotation. Notice that a linear transformation maps the zero vector to itself. We say it fixes the origin. In this sense, the translation is not a linear map. We can verify this. A translation takes the form of mapping a vector A to A plus T. Now we will check the first and second property. For the first one, if we apply the transformation T to the sum of A and B, we get A plus B plus T. And if we apply the transformation to A and B individually, we get A plus B plus 2 times T. Therefore, the translation fails to satisfy the first property of linear transformations and is not a linear map. We can check the second property and it also fails to satisfy that. Here's a quiz for you. Consider the identity matrix, which is a square matrix with 1 on its diagonal and 0 everywhere else. Prove that the identity matrix is a linear map. Now we're going to look into some examples of linear transformation. First, the scaling. We define a scaling matrix here, which uses a scaling factor S. You can see it's a diagonal matrix with S on its diagonal. And this is supposed to make any 2 by 2 vector 2 times bigger. We define the origin. We define a vector V. We plot V in this line. We apply A, our scaling matrix, to V and assign the results to A. And we plot U in the last line. So vector U is the scaled version of V. You can see here, this is V, and this is U. Let's have a closer look and see what happened. We have our scaling matrix A, and we define V to be a 2 by 1 vector. Both entries are 1. We compute A times V, and if we apply matrix vector multiplication, we get first row times this column, so we get the first row here, and second row times V again, and we get the second row. Then if we add them, we get U, which is S, and S was 2. Therefore, we get U to be a 2 by 1 vector, and both entries are scaled by S. So recall that matrix vector multiplication multiplies each row of the matrix by the vector. Another way to think about this is considering matrix vector multiplication by weighted sum of the matrix columns, where corresponding column is weighted by the entry of the vector that has the same index. Here we have first column of A, and here we have second column of A. So this way of writing matrix vector multiplication gives a way to see matrices as columnar spaces. Now let's look into rotation. We define a rotation angle, 45 degrees. And then we define a 2 by 2 rotation matrix. We do not know where it comes from, so we just accept it for now. This matrix is the 2D rotation. We define our vector V. We rotate V and assign its output to U. And in the end, we plot U and V by picking the initial point to be the origin. As you can see, this is V, this is U, which is a rotated version of V, and this angle is 45 degrees. So we can again write rotation times V in form of row times column, or weighted sum of columns of the rotation matrix. We can also numerically compute U. Next time, we're going to look into 2D and 3D rotation matrices.